One second. Today I'm going to be talking about some work that I have been doing with my team here at Los Alamos National Laboratory and with feedback from many people across many institutions, where we are pursuing new ways and new approaches to try to make enhanced geothermal systems be profitable, ideally using technologies that are available to us today. And so far, this research seems to be pointing the way towards, well, in a sense, reaffirming the high importance of multi-stage fracturing in enhanced geothermal systems, but also taking advantage of some newer concepts around fracture caging and hydropropping. In this photo, you can see me standing in front of the Puno Geothermal Ventures combined cycle geothermal power plant in the big island of Hawaii. And in the background, you can see the lava flow that came out of the Kilauea volcano, not the most recent eruption, but the one before. And you can see just how close that lava flow got to the geothermal power plant. At one point, that power plant was sitting on a rise, and it's now in a low. So it's kind of an interesting environment that they work in out there. So to start off here, we'll just quickly go over the motivation and objectives of this talk. I'm going to be a little bit ambitious here, so hopefully I don't leave too many details behind as we kind of jump from subject to subject. But we'll start off with a discussion of real-world fracture complexity using observations from the field and the laboratory. And we'll explore a little bit about the mechanisms behind this complexity. We will look at fracture caging, and I'll provide an update on some of the experimental work that we have been doing here at Los Alamos to try to validate this new concept. And then finally, we'll talk a bit about the economic potential of what I'm currently calling next-gen EGS. I know that there's other terminology out there for next generation geothermal energy and things, so maybe we need a better name, but that's what I'm calling it for now. So underlying this, as I move forward, we're going to be making progress on trying to see about the possibility of this key hypothesis that I have here in the center, where the idea is that we might be able to use fracture caging, zonal isolation, hydropropping, and modular power systems. In other words, like binary power cycles that are split into multiple different units to help enable economic power generation despite the complexity of the natural underground systems, where hydraulic fractures might interact with natural fractures and so on. Ultimately, this could help us unlock the 60 gigawatts of electric baseload power that was estimated to be possible with the GeoVision study from DOE. And if there's questions, feel free to ask them. John, if you want to interrupt me with any particularly relevant questions in chat, please feel free to do so. So I also need to quickly talk about the previous, current, and proposed approaches to enhanced geothermal systems to help set the stage for exactly what we're talking about here. So back in 1977, or in the 1970s, there was a pilot project that was led by Los Alamos National Laboratory and funded by Department of Energy to explore the concept of hot, dry rock, where they drilled 2 wells, one of which you can see they had to, or both of which they had to re-drill a few times to actually get connection between the 2 wells through fracture fluid flow in the subsurface after stimulation. But all in all, that project was, it was reasonably successful considering the novelty of what they were trying to do at the time. And then this center graphic comes from GTO's infographic on what EGS is from the the DOE website. And you can see it's a bit cartoony, but the premise is sound, where you inject in one well and produce, in this case, from 2 others. And then you have somehow stimulated rock volume that just somehow works in the subsurface. The vagueness of this bottom part is kind of key, because ultimately, if we don't do this bottom part right, nothing else is going to work. So that's going to be the focus today. So in that direction, right now, you could call it my pitch or my proposal to all of you, is this next-gen EGS concept. So the general premise is that you have a cased injection well that goes down to a sub-horizontal alignment, since hydraulic fractures at depth tend to be vertically, propagating vertically or perpendicular to minimum least principal stress. Around that injection well, the current analysis is indicating that we might need 3 separate production wells. Here you can see 2, but I got this multiplier here. So the idea is that you'll have 3 wells around the center injection well. And then using zonal isolation techniques such as limited entry stimulation from the oil and gas sector, we can potentially make the flow out of each of these stimulated zones a bit more uniform, and thereby get better sweep efficiency through the reservoir. So the key differences between these different methods are highlighted down below. And for those of you who read ahead, I think you should be good. And we'll be talking about this more later as we go. I also need to quickly introduce some key core concepts of what we'll be talking about today. The first is going to be fracture caging. So fracture caging is the idea that if you drill your boundary wells around the injection zone before you inject fluid for hydraulic fracture or shear stimulation, the existence of these boundary wells can capture the fluid as you're stimulating to prevent the fracture growth in the stimulation zone from extending too far away from the intended, targeted reservoir volume. This technique is, I'll show some examples of here in a little bit. And the next concept for number 2 is hydropropping. So normally when we look at hydraulic fracture models, we're focusing on the propagation behavior, what the pressure is, what the flow rate is, what the fracture length is, are often the primary questions, and fracture height for environmental concerns and making sure we don't produce too much water. But the hydropropping concept is a little bit different. It's the idea that you can have a fracture held open by high pressure fluid without necessarily propagating that fracture any further. In terms of standard leak-off theory for hydraulic fracture stimulation, those familiar with it will know that there is a maximum limit at a given injection rate to which you can extend a hydraulic fracture. So we're basically manipulating that combined with fracture caging to make a fracture that we have stable and hydraulically propped with no sand. The next core concept would be multi-stage hydraulic fractures, which I already talked about a little bit earlier. And then the other key concepts to keep in the back of your mind are going to be zonal isolation. So, conventionally that might be elastomeric packers. However, limited entry stimulation, where you use intentionally small perforations through the casing, actually have potentially more promise in the geothermal environment where elastomers tend to fail. And then modular power systems are another key component. I grabbed some pictures off the internet and then made them look kind of artistic, just in case there's any sort of IP-related issues related to the photos. But the key idea here is that there are companies out there, and this business seems to be growing at the moment, of creating these kind of power packs that are relatively mobile power units that you basically plumb in the hot water, plumb in the cold water, and then they generate electricity when you hook them up. When you hook up all the connections on the outside of these things. So there might be some efficiency losses with these techniques, but for reasons that I'll elaborate on a little bit later, you'll see that the reason why they're worth considering. And then finally, a key component of this presentation towards the end is going to be some risk quantification. So, kind of going back to basics a little bit, including some of the earlier studies on hydraulic fractures. We have the Warpinski experiments out at, maybe that's a little bit presumptuous to call it Warpinski experiments, but at the Nevada test site, Sandia National Laboratory, along with others, did some experiments to stimulate hydraulic fractures in a underground mine And then they came back with a road header and mined out those fractures to look at the way they actually move through the rock. And a key thing to point out here, as you can see in this photo, is that you have the borehole here and you have the hydraulic fractures in purple, but it's not just a single bi-wing planar hydraulic fracture like we normally prefer to model. The fracture is stranded, it has multiple flakes to it, and this is definitely going to influence the flow through that structure. Looking at shale in the laboratory, these are experiments that I performed back at Colorado School of Mines. You can see these hydraulic fractures and how they tend to get these pretty complex structures as they propagate through a heterogeneous and anisotropic shale rock. This particular rock is the Niobrara from Colorado. And then in a coal seam, in a coal mine, Jeffrey with CSIRO did some experiments to do hydraulic fracture studies there, similar to the Warpinski experiments. And you could see the interaction between the hydraulic fractures and bedding planes. And again, once again, the fractures are not planar, they are not bi-wing, and they're multi-stranded. And then most recently, per my knowledge, although the industry has their own data sets that I don't have the luxury of accessing, but in the HFTS, in the Midland, I think it was Midland area, the Permian Basin, we have these multi-stranded hydraulic fractures that were picked up by a slant core after a stimulation treatment. And they discovered that they had a multitude of hydraulic fractures everywhere that they thought there would be more singular structures. And they referred to this at the time as fracture swarming. So the theme underlying all of this is that fracture branching, stranding, and curving, and other complexities like this are going to be common in hydraulic fracture treatments, and they are going to affect the hydraulic properties of these fractures. So next up, I think I might have seen Bazant's face pop up here a little bit as one of the audience members, so he's quite familiar with this work. But this is the fracture branching and heterogeneity experiments that we performed here at Los Alamos National Laboratory. They were led by Wenfeng Li. And this is a key figure that he produced, and you can read more about it in the reference here, where we were trying to identify the boundary between these three different domains of fracture propagation. So the blue one is kind of the more obvious one. That's when you're injecting too slowly for the pressure to rise to the point where you actually create a fracture. So that we call that diffusion dominated. And then we have the green zone, which is the fracture branching domain, where it's possible to propagate multiple hydraulic fractures in different directions simultaneously. And then on the top, we have planar or near planar fractures. So in this case, when the viscosity and the rate are high enough, we can bring the fracture back from the more complex domain into a simpler, more bi-wing domain. And when you look at these examples here of these photos surrounding this figure, you can see the actual experiments that we performed, where you can see the diffusion dominated kind of circular flow patterns, as well as the more bi-wing hydraulic fracture patterns in red. And then some examples of what branched fractures look like in green. So, the key point here is that from using techniques like this, it might be possible to identify and quantify the boundaries of controllable properties like the injection rate and the fluid viscosity that are used for injection to induce more fracture branching or less fracture branching. And depending upon the scenario, these two different outcomes have their benefits. And I would argue in many enhanced geothermal system scenarios, the more planar, near planar fractures are probably going to be the better choice, but we can explore that a little bit more later. There's another core concept that I have realized kind of needs to be said in a way. Hopefully this block isn't obscuring the titles. So I just want to quickly point out this kind of key concept in thermo-hydraulics of multi-stage or stranded fractures. In other words, let's assume that the total cumulative aperture that's generated during a stimulation of a fracture is governed by elastic mechanics. In other words, for a given length, and a given rock stiffness, you're going to have a certain aperture, regardless of how many strands you have. That aperture will then be divided into some fractions into each strand that goes through that hydraulic fracture zone. So in this case, we'll just use a simple two strand model that I'm just going to call fracture A in blue and fracture B in red. So in this plot here, you're seeing a model of just the cubic law flow through a fracture that's split into two strands, where the aperture ratio between the two is varying. At 100%, all of the aperture is in blue. At 50%, it's an equal split between the two apertures. So when you're looking at this, you can see right away that if you have all of the aperture allocated to a single stranded fracture, your flow rate for a given pressure gradient is going to be much higher than when you split this fracture into two equal aperture strands. In electronics theory, people are familiar with this as the maximum resistance limit for when you have a parallel circuit or series circuit, I guess it actually would be in that case. But anyways, a little bit of a tangent, sorry. It's just where this idea came from in my head, at least. But here you can see that simple model. If we then extend from this simple premise into the production, the temperature curves you would get over time as you produce or as you flow fluid through these fractures into a hot rock. In this case, the rock is modeled as 275 degrees Celsius at peak and about 80 degrees Celsius for the injection fluid. So you can see, with the faster flow in this scenario here, where I'm highlighting with the arrow, this 60%, where there's the aperture of B is essentially let's call it 2/3 of A, thereabouts. In that scenario, fracture A is going to cool very rapidly, and because fracture B, I have to cut these colors backwards. Sorry, the red one should be blue and the blue one should be red. But so for the fracture that's taking less fluid, you can see the cooling rate is much slower. However, the mass flow rate through A is much higher. So when you mix these two fluids together, to put them into a power plant, for example, the net effect is that you are going to end up in a scenario with rapid cooling with even marginal differences in the apertures of these two fracture strands. So in the right plot, you can see, the 50-50 split when the apertures are equal between the two strands, you get the slowest rate of cooling and hence the highest performance if you're talking about enhanced geothermal systems. And then as you make this system more heterogeneous, you can see that it gets much less favorable very quickly with even small amounts of heterogeneity. So here, some of you might be thinking 20% heterogeneity might sound like a big number, but based on laboratory data, we're seeing oftentimes 6 orders of magnitude of heterogeneity in fracture permeability. So, here, if we just assume 3 orders of magnitude, which might be a little generous, we're talking about 99.9% heterogeneity. In other words, thermal short circuiting is definitely going to occur unless we have some sort of zonal isolation underground to enforce relatively equal flow rates into each fracture strand. And without zonal isolation, we're always going to have short circuiting. And I'll say that very definitively, even though sciences tend to be not that definitive, but so far the results are very clear on that front. If you're interested in more on this, maybe we can talk about it through the questions. Okay, so I've been talking a little bit fast, moving a little bit fast, so hopefully this will be a little bit of a breather for some. But I'm going to show here some examples of fracture caging being performed in acrylic blocks. So on the left, I'll start with things going wrong. So it did take a few tries to get this experiment to work properly. But on the left, you can see the fracture will propagate horizontally and then hit the production wells, or the boundary wells if you prefer. And yet it continues to carry on and then hit the boundary of the block. This is not what we wanted to see. We did not want to see flow outside the block on the edge. So, this experiment was almost successful, but we made a key mistake in this particular one, where on each of these production wells, we were maintaining fluid back pressure. So we had, high pressures relatively in these boundary wells. And the idea was that we would actively control the flow as it hit those wells so that we could measure how much fluid was produced from each well as the stimulation process underwent. However, the response time, the control response time of those systems that were controlling those pressures was too slow. So when that hydraulic fracture hit those wells, the pressure spiked and the fracture wasn't able to continue propagating without containment. So learning from that mistake on this next experiment, we instead had relatively open flow from those production wells. And now you can see a successful hydraulic fracture cage in acrylic at least. And I'll play this one again because it's actually kind of fun to see how the fracture doesn't exactly grow symmetrically. It kind of grows in these kind of incremental flaky patterns. But another key thing to point out here is if you can see this time bar progressing here in the video, it's important to note that the injection did not stop. So we actually continued this injection for quite a long time after successfully caging this fracture. We increased the flow rates, we increased the pressures, we shut in these wells sequentially until we only had one producing. And throughout all of that, the fracture remained caged. And this is also an example of hydropropping, because you have a fracture that's being held open by fluid pressure. And that's why you can see the dark red color, because the fluid that we injected was a dark red colored oil. But you can see the aperture is remaining open and the flow is actually going from the injection well to the producers, and yet the fracture remains stable. So in a nutshell, that's an example of the fracture caging concept. So I'll go on a little bit further. So we also wanted to explore, in the laboratory at least, the minimum number of wells that's required to successfully fracture cage. Yeah, I feel a little bit hesitant to show this video, but at the same time, it's still relevant. But in this case, when you see these two wells, you can see the fracture propagate, and it actually does successfully get caged by the two wells. But you can see that there's a lot of asymmetry in the structure of this fracture. And after we did the stimulation and we were doing hydropropping, we found that it was relatively easy to accidentally start to grow that fracture in this two well scenario. And if you think about this in like a civil engineering context or a hydrology context, where you could draw your ISO lines or your phreatic surface, you can see that the geometry is just not conducive to caging because there's no control to prevent propagation perpendicular to where these wells are in a line. So this ends up being unstable, but still successful, at least in acrylic. And on the right, I'll show an example. This one's kind of fun because it's kind of mesmerizing. But before I show it, what you're looking at here is two plates of acrylic that are just stacked like a sandwich on top of each other. And you're looking through the bottom of that sandwich. And then the edge of this plate is just open to a big tank of water. And in the center well, we're going to inject water that's colored with hair dye of all things, but it'll be blue and red alternating with equal intervals of volume of fluid in the injection process. And you can see this kind of mesmerizing pattern. So when you look perpendicular to these color bands, that's the direction of flow. And you can see that you have this very rapid flow going from the injection well to the producers. And yet, as soon as you get outside of this, basically the pressure ISO lines, you start to get in this zone where there is still some outward flow, but not very much compared to inside of this caged area. So in this case, there is going to be some outward flow, some loss of fluid, as well as some gain of fluid from the boundary if you're injecting and producing at equal rate. But all in all, this is pretty good containment compared to the other ones I could show you for injection only or fewer production wells. All right, So sorry again, but I'm going to take another leap here. Granted, there's a paper that describes this particular plot in a lot more detail in geophysical research letters. But this was some of the earlier proof of principle work that we were doing on fracture caging for injection-induced seismicity control. So in this particular work, we were using a work that involved completely uncaged scenarios with Schultz et al. This is up in Canada, hydraulic fracturing for oil and gas. And then we have Hideyori, which was a EGS pilot project in Japan. We have EGS CoLab, and then we have laboratory experiments where the physical dimensions of the block are limited, which really helps with caging. But when you look at the seismic magnitude or seismic moment as a function of injection volume, there's a pretty well-referenced study from McGarr 2014 that proposed kind of an empirical way of estimating the maximum magnitude of a seismic event as a function of the injection volume. A pretty useful equation, although not universal, obviously, but still useful nonetheless for induced seismicity risk assessment. And you can see the data that McGarr used here in the orange dots. And most of which is field data, some that includes oil and gas as well as geothermal sites. And then out here in the outlier, you have Pohang, South Korea, which is a critical stress event, most likely. And then you have Hideyori. So Hideyori actually had enough wells to kind of get towards a fracture caged system. So the interesting thing to note here is that the majority of the seismicity falls well below the McGarr line. And you can see that the maximum magnitude seismic event in terms of rupture area is smaller than what's defined by the spacing of the wells at the Hideyori site, which was about 120 meters of length, if you're assuming a rupture in well to well within that pad. So in a sense, it's possible that maybe this caging is limiting that maximum magnitude so that perhaps it can't even get above this purple line. And then in the laboratory, we see similar effects where, as you can see down here, the other characteristic of caging is this tendency to have, rapidly accelerating seismicity early on that then kind of plateaus and tapers off to almost nothing as injection continues. One other thing I'll point out here with the Hideyori that's particularly interesting is you see this plateau behavior, which is characteristic in terms of the cumulative number of microseismic events versus injected volume. You can see this little blip here at the end. This was what they called the seismicity induction test. They had so little seismicity at their site at the time, despite continuing injection, that they were suspecting that there was something wrong with their seismic network. So to make sure their network was still working, they significantly increased the injection rate and were successful at stimulating new seismicity once again. So this is actually a pretty good validation case for the premise of fracture caging for injection-induced seismicity control in its field scale. Okay, again, I know I'm jumping around a lot, or kind of making some leaps here. But next, we're going to take these principles of fracture stranding, fracture branching, fracture caging, and hydropropping, and we're going to look at what their potential is in terms of economics for developing enhanced geothermal systems. And I'm going to check the time real quick, make sure I'm not running too slow. Okay. So the premise here is, we need some sort of model to connect these dots. So we have the design question, and then the goal of, enthalpy versus time at the very minimum. So to get there, we developed the geothermal design tool, or GeoDT for short. You can see a link if you wanted to take a look at the code yourself, because it is open source on GitHub. But basically the workflow is quite simple and, kind of a linear coupling process. So we do system parameterization. We put a 3D geometry of fractures and wells. We have a geomechanics solver, a flow solver with some iteration involved in there. And then we have a heat transfer solver that doesn't couple with geomechanics. It's just a sequential. and then iterates within itself. And then we ultimately can calculate power production using Frash ranking and the binary cycles. And then through all of this workflow, at the end of a single model, it'll just print a single line in a CSV file that summarizes all the inputs and the outputs for that particular model run that are most important, which makes it quite useful for things like machine learning. So to kind of help further elucidate this process, in this video here, you'll see basically the end-to-end process with GeoDT. We start off with parameterizing populating natural fractures, and then we install the wells. The injection well here is the dashed line, production wells in blue are solid lines. And then we go through that network of fractures and identify what actually connects to the wells. So the actual connected flow system. Here you're seeing hydraulic fracture stimulation being simulated, as well as you might have seen this shear fracture pop once as it's got a little bit stimulated. And then now you're seeing the flow network that underlies that solver. It's a series of pipes, as you can see, connected through nodes. And the nodes will all track pressure as well as temperature for the thermal solver. And here at the end of the video, you can see the colors of these nodes changing as the reservoir is cooling off during the long-term production cycle. And then on the right, you can see the enthalpy versus time, as well as the power versus time curves from this same model that the video was of. And I'll show this one more time with talking a little less, in case people have an interest in seeing that. So another thing I'll point out here, at least in the power production curves, is when you're doing hydropropping, the required injection pressures are quite high. So this will result in a lot larger parasitic losses from pumping than what's typically thought to be desirable. And you can see that here in the teal curve or teal line on the bottom. So there is a lot of energy required for pumping, but the net production power significantly outweighs that pumping losses, at least in terms of thermodynamic theory, with some efficiency terms, of course. And then you can also see the binary production curve is fairly flat, while the Frash ranking drops off a lot faster. So the fact that these curves are dropping over time supports the rationale that a modular power system is needed, where you can online and offline turbines and basically power units to make sure that you're always running each of those units at peak efficiency throughout the life cycle of that project. Okay, so now we're going to go a little bit into the economics. The economics, maybe to your relief, are quite simple, although maybe too simple from some people's opinions, since you can get a lot more into the details than what I have done here. But essentially, it's important to point out the goal here. So we're not trying to predict the economic potential of a specific geothermal site using GeoDT. We're trying to have a metric that more reasonably evaluates the viability of a project by accounting for the cost of drilling the wells and the power production potential and the other capital investments that are required along that line of thinking. So really, it's just, you could think of the cost model as kind of a prospectivity evaluation to see, how worth it might be to continue forward with a given design at a given site. So I'm not going to go through these numbers. These are actually in the my ARMA paper for this year's conference, if you wanted to take a look at it there. Granted, that's not released yet, but it'll be coming soon enough. And you can see that we have electrical sales, so that's the profit term, and everything else is pretty much cost. Another thing I'll point out real quick here is we do actually have kind of indirectly and very, let's call it a preliminary way of estimating the induced seismicity risk of a given design for EGS. So we can estimate, what the maximum magnitude of event we might incur at a site during injection. And then we can use this information combined with some insurance reports based upon large earthquakes around the world. And from these pieces of information, we decided to go with a model based on Pohang 2017 and Christchurch 2011. And we choose those 2 points because they are some of the most expensive earthquakes in human history. We want the most expensive earthquakes in human history because we want an extremely high penalty function for generating any felt seismicity at an EGS site. Because if that were to happen, it would be bad not only for that particular site, but for all other EGS sites, or potentially globally, because of the negative PR that would generate. So we really want to make sure that the solutions that we choose are going to have near zero probability of shaking somebody's house. So next up, I'm going to do a case study that's based on the FORGE project. It isn't the FORGE project. I'll stress that again, because I'm not making predictions for FORGE. These are just using a very good data set that's publicly available thanks to the FORGE project to explore future concepts for EGS development. So you can see the FORGE site here. We're going to be focusing on the injection and production well, which is this dashed line along the surface trace. And then the 16B production well is not yet drilled and the location is not yet decided. So we have the 16A well that is a little bit more fixed, and we're going to be changing the depth of this well, but keeping everything else the same. Then we have temperature data, we have pressure, stress data, natural fracture data, and a bunch of other really good pieces of information for a nice holistic analysis. So from here on, I'm going to be calling this DreamFORGE, just to point out that it isn't Forge. It's kind of a fantasy version of it. And basically what we're going to be doing is we're going to be starting with the current design. And then we're going to be doing a lot of analysis based on the premise that you're most likely to get short circuiting through just a few of the stimulated zones flowing. And then we're going to try to optimize that design. And then we're going to add more wells for the fracture caging principle. We're going to increase the depth so that we get hotter rock, but also more expensive wells. And then we're going to reduce the well count to see if we really needed all of those wells. And then ultimately, we're going to do one more comparison to a sand-propped, more conventional EGS design. So this whole analysis used 31,051 simulations that were completed by GeoDT. All of these simulations took about 17 hours using my desktop computer, the same one I'm using to present on right now. And it was about 20 seconds per 30-year model. So GeoDT is a very fast model. And then the batch design variables, the key variables that were of interest, are going to be well spacing and the flow rate. So those are variable within each of these sets of realizations. And then for the stochastics, we have 41 different reservoir parameters, all of which are stochastic. So none of them are fixed from model to model. They vary constantly. The fracture properties vary from fracture to fracture. And then we have the 9 design variables, which are things like depth and flow rate, well spacing, that kind of thing. Again, you can take a look at the ARMA paper because it does have this in there. Okay, so it actually took quite a bit of effort to figure out how to make sense of this, thousands upon thousands of simulations to actually get a story out of it that we can, digest. So here you're just seeing an example of what one batch of simulations looks like for the FORGE site, its current design depth with 2 wells. And the output here is average net power per year. And then you can see that the general power output for that design is not that great. And that's primarily because it is a little bit cold as far as EGS could be. At 200C, it's kind of on the edge of what could, where it starts to become economic. And then if you go deeper and you add some more wells, you can see that the total power output is significantly higher for the same general design case. But this is really hard to make sense of. You can see the scatter, mixtures of high and low performers right next to each other. It's kind of a mess. So let's look at it using some statistics. Hopefully I'm doing okay on time. I should speed up a little bit here. So we'll be using quantile statistics. In other words, the P90, P50, P10, and others of that type, where P50 signifies that 50% of the total population are going to have a larger value than that P50 value. P90 means that 90% of the population will have a larger value. So you can think of P90 as kind of a worst case, P50 as the average, and P10 as a best case. So if you look at these statistics for power production as a function of those different designs in that box plot I showed earlier, you can see that as you add more intervals, you add more wells, you go deeper, the power that you can get out of the site keeps increasing. Then I have a repeat analysis here where I actually split this design into two separate batch runs, which each had a slightly different version of the solver being used, just to verify that the statistics aren't too heavily influenced by, not having enough samples, that kind of thing. And then we reduced the well count, like I talked about earlier, reduced the number of intervals. In other words, we don't use the multi-stage stuff effectively. We have short circuiting. And then finally, we look at sand prop again. And you can see that, less wells, less power to some extent, and then fewer intervals is a huge detriment. Without solving the short circuiting, economics of EGS are not great. So in terms of power, capital, and risk, so the risk would be primarily the seismic risk here, which is what's in this bin. And then we have the net term, of course, in green. So, the current Forge site, its goals are science. So I just want to be clear about that. I'm not trying to say anything bad about the Forge project. I think it's awesome. But right now the outlook is not great, at least by my analysis, for generating any profit from electricity sales from that site, unless there's like massive stimulus or tax or whatever that flips that equation around somehow. If you add more wells, you do get more cost, but you also produce more power. And then, going deeper, you're adding more cost, but you're also getting more power. So when you compare these effects, if you look at the green curve, you can see that we're starting to get really good NPVs at about 1,500 meters deeper than the current Forge site, where the rock is much hotter, but hopefully not too hot to be able to deploy the tools that we need to. So in terms of net present value, we get a slightly different picture when we look at the more complete statistics. Previously, I was just showing P50. Now I'm showing a much larger spread. And you can see, like on the right with the propped scenario, statistics would actually work out in the favor because the really good producers outweigh the bad scenarios. So in the long term, if you did enough different sites, you should be in the positive with this kind of a scenario, right? So this would be good for, more of a gambler, somebody who has more risk tolerant approach. And then all four of these options for 4-well, 3-well, or all three of these options for 4-well and 3-well and 2-well, you can see that they're all pretty comparable. So it's not clear which one is really the true winner when you look at it this way. So next, I'm going to be sticking my neck out a little bit. Feel free to shoot me down. So we're going to be taking a preliminary look at the seismic risk prediction component of GeoDT. And remember, this is preliminary. There really isn't a good way yet to predict induced seismicity for a given site. We use the traffic light protocol to mitigate risk, but an accurate prediction before you ever inject anything, we're not really there yet. So this is a very preliminary, very suspicious analysis. It's just meant to kind of provide some context and a way of thinking about things. But you can see here that you dramatically reduce the risk, at least with this model, of generating large seismic events by using fracture caging. So in this scenario, you have a higher probability of making sure that you get good connection between the wells, so you're not leaking off in an environment and generating potentially large seismic events. However, when you reduce that well count by even 1, this seismic risk increases significantly because there's a higher chance that you might miss your production well with your stimulation zones. And then 2 wells a little bit worse. With propped wells, it can be a bit safer in some ways because the injection pressures are lower. But the winner, according to this analysis, appears to be this green box here with fracture caging, multi-staged. I'll just go through this list actually. With multi-staged, with zonal isolation, with 4 or more wells to ensure caging, hydropropping. In this case, the reservoir is about 300 to 350 degrees Celsius. And the steeper the thermal gradient, the better. That one's kind of an obvious one because then you don't have to drill as deep, which means less well cost, in theory at least. So I'll go on to conclusions here. I'm not actually going to talk to this slide. I'd like to just go ahead and open up to questions, and then I'll bring it back to this slide again. And of course, my acknowledgements from basic energy sciences and laboratory directed research and development, internally funding, and DOE and GTO. Thank you, everybody.
Thank you, Luke. There's a lot to think about here. Excellent presentation, and we'll open it up to questions. We'll start with the chat. Can you see the chat, or do you want me to read them?
Let me see if I can access it. I'll want to keep sharing screen. Yeah, I can see it.
Okay, so the first question is from Igor Dontsov.
Okay, so regarding the fracture branching experiments, you showed that the result depends on the product of viscosity and rate. What's the value of stress anisotropy? Okay, let's go back to that slide because that is a good question. Although the paper will elaborate on this more than I did here today. So on the fracture branching slide, this term here for heterogeneity is actually the ratio between the permeability of what we call the weak layers, the W term. In other words, the permeability of the fractures, if you prefer to think of it that way, and then the permeability of the matrix for Km. So it's actually permeability anisotropy for the heterogeneity of this system, which includes this grid that you can kind of see here. And then stress anisotropy is also something else that we've looked at, but not yet experimentally in detail. That work is ongoing, and stress anisotropy is definitely an important factor here. All of these experiments that you're looking at here are more or less isotropic horizontal stresses. Okay, and then I see a question from Bizant, and let me know if I didn't answer that very well. So from Bizant, we have a number of questions regarding lab deer. I'm sorry, Bizant, can you just ask this question out loud? If you can get your mic to work. Well, John, are you able to unmute him, or?
Well, in the interim, while we're figuring that out, there is a question from.
I was muted. One question, key question I have: relationship of lab to deep rock. Now, these experiments are very useful, but you basically connect equations for individual phenomena intuitively. What happens down there? One needs to develop a comprehensive mathematical model, and there are differences which you can reflect. So on the surface, for example, you have very anisotropic stresses, overburden and tectonic stress. And when you create a crack, then you first balance the stress by fluid only, and that then dissipates that pressure difference into the rock and causes, in poromechanic sense, that load is transferred gradually from the fluid to solid. And then you get all this situation, also crack parallel stresses, which have enormous effect on fracture energy on how crack propagates. So these are phenomena that I think should be modeled. So
I agree
another
completely.
question is, which you don't have, is enormous effect of osmotic pressure, which is due to gradients of concentration of ions of magnesium, calcium, potassium, lithium, and so forth. And you mentioned 3 degrees of difference in permeability. I think they're all due to osmotic pressure effects. It was shown at Stanford a few years ago that you can get 0 permeability if you pump non-saline water of shale, because that prevents influx of water. Water flows from high salinity to low, and that's a dominant effect. That's enormous effect, and that you don't have certainly in the case of your experiments in plaster. And I think this needs to be captured by boundary value problem model, like finite element, that sort of things for the whole system. That's my view. But excellent seminar.
Yeah, it'll be very interesting to see what the other factors might contribute. You know, chemically driven fracturing as well as stress gradient driven fracturing. That's one of the more commonly understood ones for EGS, is the idea that a hydraulic fracture, due to contrast between the lithostatic gradient and the hydrostatic gradient within the fracture, will have a tendency to drive fractures upwards, which could be exploited for things like caging. But there's going to be a lot of complexity down there, that's for sure.
But even in these multiple stages, I don't see how you can get century-long or maybe 20-year productivity, because you need to create big fracture network. And I mean, you can drill and make more parallel lines, and I wonder if that will be really feasible.
Yeah, I think the Forge project actually will be a really good opportunity to explore those kinds of questions as well.
Yes.
So I'm excited to see what will come out of that.
That's true.
All right, so let's move on
Lou,
to the next question here.
If you could actually skip back, there was a question by Ali Danishi regarding randomization of in your simulations.
I don't see one from Dineshi.
So
You want to read it?
Ali, do you want to just express your question?
My question was related dimensions. Well, how long are the horizontal wells? How long are these wells? What's the spacing between them? Are you fracturing at one time all of them, or you're staging them? Just a few notes about the dimensions.
Sure. I think the video might be a good way to kind of address that one, actually. So the well spacings that we look at, at least for the Forge based scenarios, is up to about 747.8 meters. I know it's a very specific number, but actually it's just one of my favorite models of airplane, the Boeing 747-800. But in terms of practical limitations, the Forge site is underlying an alluvium, and that alluvium is about 800 or so meters above the current depth of the 16A well. So I didn't want well spacing that was so large that the wells would end up in the alluvium if they were drilled above the production of the injection well, or 16A, I should say. So that's kind of the upper limit. And then in the video, you can see the stimulation process here. You'll notice that these 4 stages are all kind of being stimulated simultaneously. That's not how you would actually want to do it in practice. But in terms of the modeling effort, doing it this way makes the models faster to execute and ultimately doesn't seem to have a huge effect on the thermal flow analysis because of the way that I solve it. So, in the end, after the stimulation, I do a circulation calculation before I do the heat transfer solution. So, this is basically just a trick to improve numerical efficiency rather than to model the exact sequence. So, GeoDT, you could split this simulation process up and stimulate each interval sequentially, or you could do perf and multi-stage stimulations. And there are a lot of different ways you could set up these boundary conditions to be arguably more accurate. But right now, from what I'm seeing, in terms of the net present value, it's not changing the answer a lot to add that additional detail currently, at least for finding designs that seem to be in the right ballpark for high producers. Does that make sense?
Thank you. Yeah, let's go ahead. Move on, please. Thank you.
Okay, and then I think the next question is from Soliman. Is that correct?
I see a
okay,
request.
Actually, that's just a request. Yep. Okay. Yes. Sorry. Go ahead, John.
No. Your show, man.
All right. Yeah. So I can make if you want to send an email to me, my email is simple. It's lfrash@lanl.gov. And I can help connect you that way. So from Nicholas Espinoza, so why thermal short circuiting does not kill EGS, even though the economics turn out to be really bad. Okay, I think maybe I had a misstatement here. So I would argue that thermal short circuiting absolutely will kill EGS. So if we go back to the economics, here you can see it a little bit more clearly in terms of net present value. So if you want to compare these scenarios in blue to this scenario right here in white, between the blue and the kind of amber color. So this is the difference between a short-circuited scenario and a non-short-circuited scenario. And you can see it's like night and day between the production potential between the two. The surface area that's actively transferring heat to the fluid is so much different when you have successful multi-stage completions and multi-stage long-term circulation that without it, it's really difficult to get these things to be economic. The benefit, of course, here is that you don't really need a whole lot of additional lateral length in order to get multi-staging to work. So the cost difference for drilling is basically nothing. There will be a cost difference for the stimulation process, of course, but without multi-stage, the economics are pretty bad. And even if you do multi-stage, there's a very high probability without some sort of in-well flow rate control to make sure that you distribute that flow to each fracture zone more equally, that short circuiting pretty much will occur with even tiny amounts of heterogeneity in the permeability of these fractures. Does that answer your question, Nicholas?
Yes, thank you, Luke.
Sorry about being unclear about that earlier.
Yeah, great presentation. I like the economics and the risk analysis.
Yeah, preliminary. Let's call it that. And then I see a question from James Rogerson. Does your model take into consideration discrete fracture networks? I'm presuming that's what you mean by DFN. Yes, you can call this a discrete fracture network model, although it's the way it's solved is as a network of pipes and nodes, as you can see in the video. So it's simplified in terms of how the solver evaluates the discrete fracture network, but it does have three-dimensional effects as far as connectivity included. Just because I assumed that was quite critical to accurate simulations. This particular scenario that I chose for the video had intentionally few connections between fractures, just because it's really hard to look at these things when there's too many flow paths in them. They look like a bird's nest. Yeah, it is a discrete fracture network, so to speak, just not really modeled the way that most people might be used to.
I think those are the questions in the chat, and indeed the time is up. Regardless, I mean, fantastic presentation. I mean, really thought-provoking, and I personally enjoyed it significantly. So thank you so much, Luke.
All right, thank you for the opportunity. This was fun.
And thanks for everyone for attending. We'll see you in a couple of weeks.